In this video, I'm going to practice some Sn1 reactions. I feel like this is one of the tougher reactions to kind of digest, more so than the free radical halogenation reactions. And so what I'm going to do is actually run through some discussion problems, and I'm focusing on discussion problems from discussion 12, number 3. Okay, so the solutions for these are on the have been posted. But again, I think it's helpful to go through. Okay, so what we're going to do is let's do products and mechanisms. I know it says don't do the mechanisms, but really it says you don't have to do the mechanisms, but really I find that I'm much more successful at predicting these products when I go through the mechanisms for each reaction. It takes more time, but more learning is done, right? Okay, so the first example has a stereocenter, which we know will not be consequential. The fact that it's a set stereocenter and not a racemic mixture is not consequential to us. So this is an example of a solvolysis reaction that uses methanol as the starting material. And if we look, we have a tertiary haloalkane. And so this is indeed an Sn1 process. And so what we can do is consider for the products, let's go ahead and draw the resulting carbocation that forms. So here the bromine is going to walk away because it's a tertiary haloalkane that gives rise to a tertiary carbocation, right? Okay, good. And then we can engage with methanol by way of nucleophilic addition of the lone pair of electrons on the methanol oxygen to give rise to this structure, which while we have an since we have an achiral intermediate, we can attack from the top face or the bottom face of that flat structure to give rise to either an enantiomer of the product. I'm just going to go ahead and avoid drawing wedges and dashes on the chiral products that result because we don't get a single enantiomer. Now what happens after methanol adds, oh gosh, I didn't draw methanol, I drew ethanol. I'm going to be consistent with my labeling of Me. What happens to the methanol is after it adds, it's going to lose a hydrogen through a deprotonation event that is different from the one that results in the E1 reaction to give rise to our Sn1 products. Now, from this achiral, and I'm just going to redraw our achiral carbocation intermediate. We have actually several vicinal hydrogens that are present. Not at the carbocation center. Come on, man. So I'm going to go A, B, and then C. So for A, what we do is we lose the carbon-hydrogen electrons are moved down to make a carbon-carbon double bond that's facing, I guess, to the south in this case, to give us product A based on my labeling. Product B results when we lose HB to form a carbon-carbon double bond. That's going to give us this structure, which is B. And then we're actually going to have two C structures. So let's go ahead and just lose hydrogen C to give us this product. Now, if you look at the EZ label for each of A and B, it's not applicable. But for C, we have what looks to be an E alkene, right? We could label 1, 2, 2, 1 gives us an E label. So if we have an E isomer, we must also draw the Z isomer And so this is our Z isomer. So we form 4 E1 products, and then I guess a racemic mixture of Sn1 products, but just a single constitution of a product. And so that is the first example. So that's reaction A. Luckily, that one was actually sufficiently complicated. I probably don't need to go through all of these. I'll sort of pick and choose. Maybe, well, they're all kind of interesting. Okay, so B, let's go through B. So B, we're going to switch the nucleophile away from methanol and go into water. And so what I want to do right away is just let the bromine fall off to form a carbocation. Now, maybe it's helpful to, in this case, draw a hydrogen present. This is a secondary haloalkane, but it's next to a benzene ring, so it's likely to form the carbocation intermediate nonetheless. So now we can engage this molecule. It's actually easier to draw the E1 product. So we could have hydrogens from this position come down to make the E1 product, which is this. If you look, this is E, so we need to also include Z. All right. So with that done, so here's my E and Z. So these are my E1 products. Right here. Good. Okay, now for the Sn1 products, we again consider the carbocation intermediate. The single stereo center, the single stereo isomer drawn for the starting material is not consequential to the products because we will form a racemic mixture. Now, in the case of methanol, we have the oxygen attack and the methyl and the hydrogens come along for the ride. Here, we're just going to have 2 hydrogen atoms that come along for the ride. And then one of them is going to get lost from this intermediate structure. So we're just going to let the hydrogen fall off, and that's going to give rise to this as our Sn1 product. Okay. Now I show it as a straight line because it's a racemic mixture. Next, we'll go through C. So in the case of C, we have a stereocenter, which is defined as a wedge. Notice that is not part of the haloalkane. If it's not on the CX bond, we need to leave that stereocenter alone for the most part. Now we're using methanol again. The first step is to lose the halogen atom. I don't feel like we might have to apply some heat if we actually did this in the lab, but that's not a big deal to us right now. We're just trying to push arrows and make sure we understand overall transformations. In this case, I'm going to start with the methanol as the Sn1 nucleophile. So the electrons come in and neutralize the positive charge, but render now the oxygen with a positive charge. Now, after the oxygen adds, we're going to have to lose a hydrogen atom by dumping the electrons between the oxygen and hydrogen bond between the oxygen and hydrogen bond onto the oxygen atom to neutralize that positive charge and give rise to our new product. But notice, we don't have a racemic mixture. In fact, we have a single enantiomer in this case because the stereocenter that defined the chirality of the molecule was not involved at all in our Sn1 reaction. It will be slightly in the E1 reaction, but we'll look at that and we'll see why it's not a big deal. But anyway, so here is the outcome for the Sn1 reaction. Okay, so E1 reaction of C. Now what we're going to do is redraw our carbocation intermediate and consider the vicinal hydrogens that are nearby. And so the vicinal hydrogens are A, and actually if you go down here, this is also A, so we only have to do one of them. And then we have B. Now B is at a stereocenter, which makes this awkward, but let's lose A first. So the electrons between the carbon and hydrogen bond, labeled at HA, are going to move down to make a new carbon-carbon double bond. And so this product A could be formed by losing the HA that's pointing directly north, or I suppose southeast. Either one of those would give rise to the same product, because free rotation could move that double bond around, not over the double bond, but the thing over this bond. Okay, so that's product A. Now, what about product B? So in product B, we're going to take the electrons between the CB bond and move them down to form a carbon-carbon double bond between the what was the stereocenter and the carbon with the positive charge. That's going to give rise to product B. Notice that product B is not chiral. It does not have a stereocenter anymore. And if you look, we actually got rid of the wedge and the dash at this position because it is now sp2 hybridized. That is, it has a carbon-carbon double bond. If it has a carbon-carbon double bond, we don't add wedges and dashes to it unless we're trying to show something really special, which you won't from me. So as a result, the wedge and the dash are gone. Now, neither one of these products has an E or Z component to contend with, so we're actually done. We've drawn all of the Sn1 E1 products. Okay, D is actually fairly similar, except that we have a stereocenter in the haloalkane. So it's worth doing, but there is a nuance to it because it's a ring. It's worth mentioning. So with this molecule, and ethanol, what I'm going to do is I'm going to skip through some of the details of the Sn1 process, allow us to form a carbocation at the position that had the halogen, which was the iodine, by a spontaneous heterolysis reaction. And then with top or bottom face attack, we could form either configuration at the position that had a positive charge. I'm just going to draw it with a straight line as opposed to defining a wedging, a dash, which I would have to draw for both. Hydrogen's going to fall off. That's going to give rise to our Sn1 product with one stereocenter that remains defined because it was not participating in the Sn1 process, and then another stereocenter which did participate and is now, that stereocenter is racemized. No, we don't have a racemic mixture in this case. We have a mixture of diastereomers, but just drawing the straight line is all that you need to do. Okay, so if we skip on to the E1 reactions onto the next page, you'll see we just want to look at something that's it's at least worth mentioning. So what I'll start with E1 reactions are on letter D, is that what we could do is we should recognize that, how do I say this? That it's hard and unlikely. It's hard and unlikely that E alkenes form inside rings. Okay, let's look at that. So with this as our carbocation intermediate, we actually have 3 hydrogen atoms that are vicinal to the positive charge and would give rise to then 3 alkene products. The first one is noteworthy because it destroys the stereocenter that was defined as a wedge. We form a carbon-carbon double bond extending from the positively charged carbon to that carbon that was a wedge and now is a chiral sp2 hybridized and does not have a wedge or dash character. Okay, if you look at this, this is actually a Z alkene, but it's in a ring, so no E. Now, I mean, what would an E alkene even look like? Okay, so we have like this, and then we have to somehow find a way to connect No. Okay, that's too unhappy. This ringed molecule with 6 atoms wants to be a hexagon. So there's no E alkenes in the rings that I will provide for you. Now, it is possible if the rings get big enough, like 8 or higher, you can actually see some trans or E alkenes inside of the rings, but that's not anything we need to worry about in this class. Okay, so we have the Z alkene only, and then if we draw, so that's product, I should add that's product A. Product B, we're going to see the alkene sit outside the ring. And if we had a more complicated substitution pattern, we could have this be E or Z if it was applicable. It's not applicable in this case because there are 2 hydrogens attached. Okay, and then if we consider C would involve, if B was loss of the B proton, C would involve loss of this proton. That's actually not going to, just like B, that's not going to impact the other stereocenters. So we form, we keep that wedge in place. And then just like before, there's no E product. We only have the Z because the Z allows us to form a clean hexagon in the ring system. Okay, if you could just look at F and G, maybe I'll give you a second to catch up on the writing. I think these sort of continue on with what we were looking at before. So it's noteworthy, there are some E2 reactions I should tell you all about. There are some E2 practice questions in number 12. So I'm going to stop sharing that screen and I'm going to share my internet window. Okay, so I have discussion 12 in front of us. So F is just another example. I won't take any more of your time. I'll let you practice on your own. In G, this is probably a little too unwieldy for the learning module. If you want to practice it, it's interesting. But in the first step, I have you do a free radical halogenation to generate all of the monobrominated products. And then from there, you're going to treat that with methanol to try to do some Sn1 E1 reactions of each of those brominated products. It's a little bit big to use. Okay, to say the least. All right, so with that, I'll cut this video out. I would say practice F for sure, maybe look at G. And it's, more examples are always better than fewer examples. But otherwise, we'll call it good for the Sn1 E1 reaction on its own for now.